बढ़िया. So we are now in exercise chapter 2. Chapter 2, exercise 2.1. We have discussed till now an algorithm called insertion sort. What it does is it sorts an array of numbers, very similar to how you would sort a deck of cards. What it does is it takes the first element, puts it as it is, then it takes the second element. If the second element a2 is less than a1, then a2 goes in front. If a2 is greater than a1, then it goes behind. So now you have, suppose a1, a2. It takes a3 from here. If a3 is greater than a2, a3 goes here. If a3 less than a2, a3 is then checked against a1. If a3 greater than a1, it goes in the middle. If a3 less than a1, it goes in the start. And this is like a case by case measurement. So basically what's happening is out of all the elements that we have, a1, 2, 3, 4, we're sorting suppose till 4, then these guys will remain sorted and the next element will be put in a placeholder inside this sorted sequence. This is called an invariant loop, I think, or sort or part or subsequence, something like that. So let's look at the first exercise. Using figure 2.2 as a model, illustrate the operation of insertion sort on the array 31, 41, 59, 26, 41, 58. So now if we look at 2.2, this is 2.2. So yeah, I think we can do this. So first let's take 31 as it is. Now 41 is greater than 31, so it comes here. Now we are 31 and 41. Now 59 is, first we put it here. Since it's greater than 41, we keep it here. 26, first we put it here. It's less than 59, so first it goes here. We have 31, 41, 26, 59. It's less than 41, so it goes here. 26, 41, 59. It's less than 31, so it goes here. 26, 31, 41, 59. So this is our current sequence. Next number is 41. Another 41. Yeah, so first we put it here. It's less than 59, so goes here. 26, 31, 41, 41 and 59. Since it's equal to this, it won't move now. So now we have this sequence, and the last number is 58. It goes here. It's less than 59, so it goes here. 6, 31, 41, 41, 58, 59. It's less than 41, greater than 41, so it stays, it doesn't move. This is our final sequence. So we're sequentially comparing it to the next number, then the next number, then the next number, and this is done using a loop where like int I is a variable. It's a complex loop. Rewrite the insertion sort procedure to sort into non-increasing instead of non-decreasing. Non-increasing is decreasing or equal. So we arrange a1 to an into b1 to bn, b1 greater than equal to bi greater than equal to bj, I greater than j, bi belongs to ai. Okay, so what do they want? If they want procedure, let's see what they mean by procedure. Will this be a procedure? Oh, let's copy this and can we select text? Yes. Copy and we can paste here. Control V. This is not very intelligible. Let's make our own. So first let's write insertion for non-decreasing, increasing or equal. For j equal to 2 to a dot length. A dot length is the length of the set A. A is basically this set. For this, perform assign key to be equal to aj. J, we are doing this for every j, so key will change in each loop. And let's put I equal to j minus 1. So ai will be the element we want to check against, and key is the element we are checking for. So while I is greater than 0 obviously, and ai is greater than key, that means in our initial sorting, let's clear up some space. Why can't I choose the eraser? For some reason eraser is now not allowed. Stroke eraser, yeah. So in our initial sorting, this step basically where we had, say, no, I can't choose this. Yeah, no. What's happening here? Why can't I choose? Okay, done. So basically what this step means, what it means is we have aj as an element, and we have till a1 till aj minus 1 already sorted, right? As we know, the initial is sorted, then we continue with the rest. So this we are calling key, and this is like ai. So it's saying while this is greater than this, take this here. Okay. As you'll see, while ai is greater than aj, ai plus 1 is equal to ai. ai plus 1 is, in this case, in the first step, actually aj. So what it's doing is, we have a1 AI, and then we have AJ. So if this is greater than this, put this equal to this. Now check for the next, if I am not wrong. I plus 1 equal to AI. No, AI plus 1 nahi. Sorry. Let's think about this again. So we have AI plus 1 equal to AI. In the first step, AI plus 1 equal to J minus 1 plus 1 equal to J. So AJ equal to AI. So okay, so what yeah, so what I think is happening is we have till from A1, A2, AI, this is AJ, and here we have to assign something called AI plus 1. It can be one of two things: either it can be AI if AI is greater than AJ, or it can be AJ if AJ is greater than AI, because the one that's greater will come later. So what it's saying is, if AI is greater than key, which is AJ, put AI plus 1 equal to AI. So take this here, okay, and then assign to the variable I the value I minus 1. So we're not tampering with what the value of j is as fixed. So now I is I minus 1. So we're now checking for the previous element, and we're doing the same. First we check if this is less than key, greater than key. If it is greater than key, then this will be assigned the value of this, and we can do this because the value of this has already been assigned to this. So currently these both hold same values. Now we're reassigning this one to be this, and now these both are same. These both are now same. And now we check for this. We check if this is greater than key. If it is, we assign this. If it is greater than key, I think we already checked for this. Now we check for AI minus 2. If it is greater than key, we send it to AI minus 1. Otherwise, we put AI minus 1 to be equal to key. That's how the algorithm will work. Now we have to work on one which is non-decreasing. Non-decreasing implies increasing or equal. Well, the first solution would be solution 1, sort in increasing, then reverse. But that's not an efficient solution. Let's look at a better solution that's grassroots level. So what we'll do now is A1, A2, A3, AN. First we'll put A1 here, then we'll take A2. If A2 is greater, it goes here. If A2 is less, it goes here. If it's less, it goes here. We have non-decreasing. No, we should have non-increasing, I think. Non-increasing, right? Okay. So we'll non-increasing. increasing, decreasing, or equal. So I'll repeat. A2 checked against A1. If less, goes in front, goes here. In if greater, goes here. Now let's write the pseudocode for this. We can copy, right? So let's see. This step is same. This step is same. We have to close. Okay, we didn't write the full code, right? What happens when AI is equal to or less than key? AI plus 1 equal to key. We can also probably run it. We'll run it. Our code and see if it works. The one we write. Non-decreasing. So I'll open the initial code here. So basically I have A1, A2, A3, AN, A is equal to this. For J equal to 2 to A dot length, key is equal to A dot AJ, and while, no, let's assign I now, I is equal to J minus 1, while AI is greater than the key do you want to have greater or lesser? I think lesser should work, no? Yeah, we should have lesser. While AI is less than the key. So if the element already existing in the row is less than the one coming in, we want this to be decreasing. So this is going here. So we assign AI plus 1 to be AI because we are moving this one step further. Plus 1 equal to AI. Then we have I equal to I minus 1. And then we can have also I greater than 0. And when AI is equal to or greater than the key goes here because it should decrease. At that point, AI plus 1 is equal to key. So this is my code. We can check the answers or we can run the code. Let's run it. Python execute. You can do it in Google Collaboratory. So we have non-increasing sorting algorithm inversion style. So let's define a list and let's give the numbers 51, 65, 78, 11, 23, 1024, 67, 34, 889, and for j greater than 2, yeah, other code like this. For j equal to 2a dot length. So we can have for j in range 2 comma len a. This is just Python syntax. For this range, let a j be the key, the one we change, and let I equal to j minus 1, the previous index, and while I is less than the key, it is, if it's greater, yeah, we just assign it later. If it's less, we shift stuff. So then we put a I plus 1 to be equal to, there must be an issue here, because if we're tempering, no, we can reassign ai plus 1. ai plus 1 actually right now holds the value of key. I plus 1 is j, but since we've stored it locally somewhere else, we can tamper. So ai plus 1 equal to ai, and I is equal to I minus 1. So we iterate backwards. So we also need, it should be like this, and I is greater than 0. Do this, and once this ends, a I plus 1 is to be assigned to key. Let's see if we get some error. Key is not defined. Oh, assignment is wrong. Key, we should rather have key equal to aj. Key equal to aj. Yeah. And now, okay, wait. Let's insert a cell here where we write the value of a, and then we again write the values of a. So we have here this. So a is currently this list. Now when we run the code, a is now the same list. Very nice. Stuff did not happen. Are we even going inside the loop? Print dot. Yeah, we're going in this loop. Are we going in this loop? We are going in there. What happens if we do this? Hitting again. Let's just put print a here. Let's check what's happening inside then. Let's print the key first. Key is what the hell? Key is this. Print I is let's print a I plus 1 is key is 78, I is 1. 78? Why are we still? Okay, so in Python, I think the indexing starts from 0. So we should have this equal to 1, I think. Key is 889. Key is 65. Yes, as it should be. I is 0. So we're not coming in here because we did have some rearrangement. It's executing thrice. Our code is apparently wrong. Let's check. For j equal to 2 to a length, key equal to aj, I equal to j minus 1, while ai is less than key and I is greater than 0, ai plus 1 equal to ai, I equal to I minus 1, ai plus 1 equal to key. Are we assigning? We're assigning. This should be correct. Let's check the solution. Chapter 2. For j equal to 2 to length, key equal to aj, I equal to j minus 1, while I is greater than 0 and ai is less than key. ai less than key. Do ai plus 1 equal to ai. What we did. I equal to I minus 1, we did ai plus unequal to key. We did. So our code is correct. There's something wrong with Python. There's also something wrong with, I think, this collaborative stuff, because it remembers previous code. There are some changes though. There's some problem with Python then, I guess. So there's something up with the Python variable equals, no, that's to compare. Our code is correct, as we saw. Maybe it's something with Python's while loop. Let's try the next exercise then. Didn't go to sleep, bro. So, just a minute. So let's move on to the next one. Maybe this works in C. C++. Consider the searching problem. A sequence of n numbers a equal to a1 to an and a value v input. An index I such that v equal to ai for the special value nil if v does not appear in A. Write pseudocode for linear search which scans through the sequence looking for V. Loop variant, prove that your algorithm is correct. Make sure that your loop invariant fulfills the three necessary properties. This part I did not understand, but I can show. These are the three necessary properties. Initialization, it is true prior to. Let's write them. They said it's similar to induction in math. True prior to first iteration. True before iteration. Terminates plus gives useful property. Okay, useful is very subjective. So input v comma a1 an equal to a, put I such that ai equal to v or 0 if V does not belong to A. Pseudocode, which scans through the sequence looking for V. So for J in for J equal to 1 to A dot length. So it starts from the first element to the last element. J equal to 1 to J equal to, no, we don't even need to do it for all, na? Can we end loops midway? Yes, we can. Or we can do it differently. Let key equals A1 while key is not equal to V. Key is equal to key is equal to and let I equal to 1. No. Okay, no, that's not gonna work. I was hoping we could define I then iterate. We have to iterate with a for loop only. Assuming we can end, first let's assume we can end in between. For J equal to 1 to A dot length. If J Aj equal to V, return J. Yes, that works, right? Else pass. Pass means do nothing, go back up. Then it comes again. Then it goes for J equal to 2. Is Aj equal to 2? And let's assign J to be 0. And return J. It's not efficient because we're returning J twice. We can modify this to go yeah, let's modify this. First, if Aj equal to V, then just return J. Else, if J equal to A dot length, if we're already on the last element, we return 0. This should work. Loop invariant. I did not use a loop invariant. So So if we were to define it theoretically using a loop invariant, how it would go would be कि we would have this a1, a2, an, then we would like first we check for a1, a2, a I, j, and we have a j plus 1 till an left. So what they're basically saying is this section is the loop invariant. Basically now we cannot be equal to any of these, and this section is equal is what we have to still check for. So using a loop invariant, prove that your algorithm is correct. Make sure, is it true before iterations, my algorithm, before any iteration j equal to 0. How can an algorithm be true? Yeah, so before any iteration this loop invariant is empty, and none of the elements in loop variation are equal to v, and v is not empty, so it is true. Second condition was true before the next iteration. Yeah, it's obviously true because we've already checked for this. And terminates to give useful property. Yes, when it terminates it returns j to us, or it returns 0. That's the only way it terminates. Because on the last element we've set it to terminate ourselves only. Let's check the official solution also. On each iteration of the loop body, the invariant upon entering is that there is no index case for that. Yeah. So this guy pre-assigned I to 0 and only changed it. Okay. So what they've done is very similar, I think. They put I equal to 0, then they said so he can reference I inside. Okay, that's alright, then I can also do it for j equal to 1 to a dot length. If aj equal to v, I equal to j, and just let this run, and in the end return I. This is away from the loop. So basically, if at any point this if statement becomes true, I becomes j, but then we're still processing further, so we can put return I here also, then we return I, and if it doesn't happen then we return I. Does happen, we return I, twice, doesn't matter. Very similar. So what else does it have to say? Consider the problem of adding two n bit binary integers. N bit matlab meaning n bit is I think 2, 0 or 1. No, binary is 0 or 1. N bit meaning 0 1 0 1 1 1 0 1 1 1. This is N, I guess. Let's check. N bit. What is N bit? Bit. Binary digit 0 or 1. Yeah, so we're right. N bit is an integer which has like 0 ones and there are n digits in total. Adding first digit should be 1, I guess. Two n-bit binary integers stored in two n-element arrays A and B. The sum of the two integers should be stored in binary form in an n plus 1 element array C. State the problem formally and write pseudocode for adding the two integers. Problem formally you'd be input and output. Input A an set B a list array Bn such that AI, Bi belong to the set containing 0, 1. A1 equal to B1 equal to 1. Let's assume, okay, there are two cases where we allow initial to be 0 or 1, doesn't matter. Let's allow, because that would make our case more general. This would work for 1, 2. So we have this, and output should be C1 to Cn plus 1 such that the number C1, C2, Cn plus 1 is equal to Ci belong to 0, 1 is equal to A1 to An plus B1 to Bn. This is the problem formally. Write pseudocode for adding the two integers. So in binary, the way we add is 1 1 0 1 0 1 1 0. Suppose we want to add this plus 0 1 0 plus 1 1. 1 plus 1 goes to 0 and we carry over 1, and we have 1 plus 1 which again goes to 0 and we carry over 1. Binary is basically 1101. In decimal is I think 2 raised to power 4 1 plus 2 raised to power 3 1 plus 2 raised to power 2 1 plus 2 raised to power 1 0 plus 2 raised to power 0 1. So we have 8 into 1 plus 4 into 1 plus 1 into 0 plus 1 into 1. So we have 8 plus 4 plus 1 to 13. This is 13. So basically we are doing modulo arithmetic. I think if we were to confirm our answer, 0 1 1 0 is obviously 0 plus this is 4 plus 2 equal to 6. So we have 6, and the answer that we got 1 0 0 1 1 is 2 raised to power 4 1 plus 2 raised to power 3 0 2 raised to power 2 0 plus 2 raised to power 1 1 plus 2 raised to power 0 1, which is 16 plus 0 plus 0 plus 2 plus 1, which is 19, which is also equal to 13 plus 6. Yeah, so we did the correct addition. So Now we need to write an algorithm to add these two. So we need to somehow, how do we define the concept of carryover? That's what I'm thinking about. We can use standard addition. I don't want to directly use modulo arithmetic. It's a good problem. So let's assume a is equal to 1, 1, 0, 1 and b is equal to 0, 1 and 0. So we have to start from the last digit. Let's first define the last digit. So our counter. So j is equal to a dot length so if one of them is 1 and the other is 0, you obviously get 1. If both are 0, we get 0. 1 0 we get 1. 0 1 we also get 1. 1 1 we get 0 and a carryover of 1 to the next one. Okay, we can do this. So what we'll do is we'll start from the last digit. Let C and we'll reverse C later, I think. So let J be a dot length. Now let C, let's suppose we can define later elements of the array. No, let's define C to be 0 0 0 initially only, n plus 1 elements. Now let C j plus 1 Cj plus 1 equal to so before this we can have a loop. First let's just reverse. Should we reverse them? Add them, then reverse it again. Let's j equal to a dot length, and while j is greater than 0, so we can come till 1, lowest value. C let's set carry over to be 0, carry equal to 0. Do we want carry to be 0? We'll see. So we'll define sum equal to aj plus bj mod 2. Okay, instead of this, let's do this. If aj into bj is equal to 0, basically these three cases, these three, if this is 0, then sum is equal to aj plus bj standard, else sum is equal to 0 and carry equal to 1, because this only happens in the case where both are 1 and we get a carryover of 1, and we haven't defined carry before. Now when we go to the next, we'll have we can have plus carry here, and we can define carry to be 0 before this, and after the sum is done we define carry to be 0 again. So to start with, carry is 0, sum is done, carry is added. If for the first three points 0, yeah, and if we come to this, sum is set to be 0, carry is set to be 1, we go back up. Okay, we also have to set j equal to j minus 1. J is still greater than 0, so now we come to this, sum is equal to aj minus 1 plus bj minus 1 plus the carry, which is still 1. Sum is calculated. Now we also have to set c. You have to set c, right? Cj minus 1, no, Cj equal to sum. We can straight away put, okay, we should put it here, and Cj equal to sum. So one of the two is performed, Cj is assigned. So this will happen till j1, and if at j1 we get this case, this will work fine, I guess. No, there's an issue here too. There's an issue here. There's an issue because if their sum is also 1 and we have a carry of 1, sum will be equal to 2, which is also not allowed. So another approach we can take is first convert binary to decimal, add decimal, then convert decimal to binary again. We can also do that, but since the computer works in binary, we should be able to do binary. This is a very good problem. So we need to define a function here, I think. We cannot do it with purely procedural programming. Let's do some functions now. Let's define a function add, takes 2 elements, a and b. If into b equal to 0, return a plus b. If else return 0, comma 1. This is basically the carry, comma b 0. So basically we'll return the sum, the one we have to assign, and the carry, to assign and carry. So now if we rewrite our code, we have a as a1 an, b as b1 bn, and c as 0 j equal to n is basically dot length, and now we start for j greater than 0. C j, initially j is equal to n. We should have while j is greater than 0. Cj is equal to add, and let's put carry to be 0 initially. Add aj, comma bj and carry. So what we're doing is we're adding aj and bj. It will return to us, and to that we're adding carry, but it is returning 2 items. How do we add those? This will give us an error. No, you shouldn't put carry here, no? This is enough. Add aj and bj. This will return us what we have to. No. Wait. Yeah, this is wrong. How we'll assign is cj, comma carry equal to add aj, comma bj. So this will return what the value is and what the carry is. So we have assigned that. Cj, comma carry is equal to add aj, comma bj. How do we incorporate carry to the next? Basically, nahi. Let's try adding again. I'm adding these, add, okay, adding these, add, okay, adding these, get 0 and a carry. So first I'm adding the carry to A wala, adding that here, I get 2, which I know is 0. 0 plus 0 is 0, and I'm taking the carry here, adding it here. 1 plus 0 is 1. Okay, so if I look at my own thought process now, which is what I've not been doing and doing it implicitly, is adding the carry to the next element of A. So we defined add to be if AB equal to 0, return A plus B basically it's gonna be 1, or it could be 0, return A plus B comma 0, else return 0 comma 1. So I'm getting a carry from adding carries also. This is difficult. So add this to this, right? Add the carry here. Carry is 0. Add this to this, right? Take the carry there. Carry is again 0. Add carry to this. Is still 1. Add 1 to 1, 0. Carry is 1. Add carry to this. 1 plus 1 is 0. Carry is 1. 0 plus 0 is 0. Add carry to this. 0 plus 1 is 1. 1 plus 0 is 1. So we have to globally define carry and add carry to the A set. Let's rewrite our problem again then. A equal to A1, AN, B equal to B1, BN. So what we'll do is, and we have add A comma B returning us if AB equal to 0, return A plus B comma 0, if into B else return 0 comma 1. This is how we've defined add. Now let j equal to 1 for j greater than 0, while j greater than 0, c j comma carry is equal to add aj comma bj. So we're adding these two, and this goes to cj and the carry goes to carry. Now we add the carry to 8th. Now we redefined. Now a j minus 1 is equal to add aj minus 1 comma carry is equal to add so when there's a carry of 1, this is 1. So what happens in this case? So this is 0, carry of 1. 1 plus 1 is 0, but there's still a carry of 1. Instead of adding it here, I should add these two and add the carry to that. Yeah. Wait. I add these two and add carry to that. That can have further carries. Right? Yeah, it can. So initially let carry equal to 0. Let's rewrite. Initially carry equal to 0, Cj equal to add Aj, comma Bj. We add those two, then we add carry to that. Here we have Cj, comma carry. Yeah, and we repeat this. This should work. And let j equal to j minus 1. And after this end, Cj plus 1 is equal to carry. And this runs while j is greater than 0. Okay, should we test this in Python? Python compiler. So let a equal to 1 comma 1. What was our example? Because we know the answer for that. 1101 b equal to 0 comma 1 comma 1 comma 0. J equal to len a while j is greater than 0. And c is equal to this greater than 0. Okay, we have to define add also. Define add a comma b if a into b is equal to 0, return a plus b comma 0, else return 1 comma 0. No, here we have 0 comma 1. While j is greater than 0, c, and we define carry initially to be 0. Cj is equal to j comma carry is equal to add aj comma bj and carry j equal to j minus 1, and then we define c. Okay, in Python let's define it to be the length plus 1. No, I think this will give us some error initially, so we may have to do plus 1 or minus 1. and C0 to be carry. Then we print C. Line 14. List index out of range. C, where is C? What's our actual answer? Is this close? Actual answer was 10011. So we don't have ones here. Let's print C at each point. Print C. And the carry. Carry is 1. Let's see the solution then. This is the solution to linear search for. We did the same, yeah. Carry equal to 0, very similar to ours. For I equal to n to 1, this is reverse. Okay, we can do this, that's cool. Ci plus 1 equal to ai plus 1 plus bi plus carry mod 2. If plus carry is greater than equal, then carry equal to 1, else carry equal to 0. This is pretty similar. C1 equal to carry, yeah, we did the same steps, I think. There's some problem with the for loop of Python, while loop. Can I put this to for? There's some problem with the loop. So this is also addition mod 2, basically. Let's write this code now. Not easy, definitely. So what they did was carry is 0 for I12 and to undo Ci plus 1 equal to ai plus b. I plus 1. Yeah, okay. Yeah. Okay, we should have done I plus 1 too. Yeah. That's the main issue. Cool. We were not able to do this one on our own. Let's try it again now. First I'll see if the reverse loop for loop runs in Python. For I in range 5, 1 print I. No, this doesn't work. Reverse for loop Python backward iteration. Okay, so we have to put a -1 here. 5, 4, 3, 2. This one will not be hit. Okay. Now this should work, or we'll put a -1 here. I'm going to do it mod 2. And if ai plus bi plus carry greater than or equal to 2, or 3 can be 1 also, right? Carry equal to 1. In the case that it is 2, carry is 0, isn't it? No, carry is 1. In the case that it is 3, carry is still 1. I think, because we have 1 plus 1, 0 plus 1, yeah, and else carry equal to 0. Is there something else? C0 carry print C. Line 7. Let's just check which I is causing errors. It starts from I equal to 4 and there is an error straight away. C5 does not exist. Okay. Yeah, because I is equal to 4 and C 4. Because indexing in Python starts from 0, which is a dumb rule. Maybe we can put this as equal to -1, or instead of changing it there, just put this as equal to -1, run it. One zero one one zero. No. What we should be getting is 10011. Let's print C at each point. Okay, so I didn't add the carry at this point. This is also incorrect then, because if the last two elements are 1, the answer should be 0. So I added it wrong. Okay, this is 0110. This is different. Answer is still wrong though. 1010011. We got the correct answer. Yay! 10011. Yes. Let's check some other numbers. 1100. 0101. What is this? This is 100101. Let's check this. 1100. We have 1100, and here we have 0101. Now the answer is 10001, which is also what we got. Nice. Done. So now we have these problems. So this is done. So now we'll meet next time. Sukriya, thank you.